the fragile chain that made Earth habitable. Rare events that made Earth habitable. The Goldilocks chain, from space to life. Earth's habitability looks simple from a distance. A rocky planet at the right distance from its star, with liquid water and an atmosphere. But that picture hides the real story. Earth habitability is not one condition. It is a long sequence of filters that had to line up across astronomy, geology, chemistry, and biology. The central tension is that many Goldilocks factors are not fixed settings. They drift. Stars brighten, atmospheres leak, orbits wobble, continents rearrange, and life itself rewires the air. So the real mystery is not how Earth became habitable once, but how it stayed habitable long enough for complexity to appear. By the end, you will understand the main rare events and stabilizing mechanisms that kept Earth in the narrow corridor where oceans persist and complex life can evolve, plus the key uncertainties about how common that corridor really is. The story turns on whether habitability is mostly luck, or mostly feedback loops that make a lucky start endure. Key points. Earth's habitability is a chain: star type, orbit, planetary mass, water, atmosphere, magnetic shielding, and long-term climate regulation all matter. The Goldilocks zone is necessary, but not sufficient. A planet can be in it and still be sterile or unstable. The moon likely mattered twice. First, by how it formed, and second, by how it influences Earth's long-term axial stability and tides. Plate tectonics and the long carbon cycle act like a thermostat over geologic time, limiting runaway freezing or overheating. The early sun was dimmer, yet Earth avoided permanent freeze. That implies strong climate buffering and/or greenhouse conditions early on. Oxygen was not there from the start. It rose in steps. And those steps reshaped what kinds of life were possible. Impacts are double-edged. They can deliver volatiles and nutrients, but they can also sterilize or reset ecosystems. A single asteroid impact did not create life, but it may have reshaped the path to modern ecosystems by clearing ecological space. What it is. The rare events that made Earth habitable are the low probability conditions and historical accidents that allowed a rocky planet to keep surface liquid water and an environment stable enough for billions of years. This includes cosmic setup, where the planet formed and what orbited nearby, planetary properties, mass, atmosphere, internal heat and magnetic field, and deep time transitions, oxygenation, climate regulation, and evolutionary breakthroughs. What it is not. A claim that Earth is unique, or that life elsewhere is unlikely. The rare part refers to a specific combination that supports long-lived surface oceans and complex, energy-hungry life. Microbial life might require a different, possibly wider, set of conditions. How it works. Start with a simple idea. Habitability is a stability problem. You need liquid water, not just for a season, but across planetary and stellar change. First comes the star. A stable, long-lived star gives chemistry time. If the star is too massive, it will burn out quickly. If it is too small, its early activity can be harsh on planets that are close to it. Next comes orbital placement. The habitable zone is a distance band where a planet could, in principle, maintain liquid water on its surface. However, the phrase could, in principle, carries significant implications. Atmospheres can push a planet toward a runaway greenhouse or global freeze, even inside the habitable zone. Then comes the planet's build. A planet must be massive enough to hold an atmosphere and keep internal heat, but not so massive that it locks into a different evolutionary path. Its early collisions shape its rotation, its core, and often its satellite system. Thereafter, long-term regulation takes over. On Earth, rock-water carbon chemistry and plate tectonics recycle carbon between the air, oceans, and crust, This matters because the sun's brightness changes over time. A planet needs a way to compensate. Finally, biology becomes part of the machine. Life does not merely adapt to the planet, it changes the planet. Photosynthesis, oxygenation, and biological carbon burial transform the atmosphere and surface chemistry, creating new possibilities and new risks. Numbers that matter. Earth's age is about 4.5 billion years. That number matters because complex life appears to require long continuity, stable oceans, repeated recycling of nutrients, and enough time for evolutionary experimentation. Earth's axial tilt is about 23.4 degrees today. Tilt controls seasons and the distribution of sunlight. If tilt varied wildly, climate would swing harder, stressing long-term stability. The early sun was significantly dimmer than today, on the order of tens of percent lower luminosity early in Earth's history. Yet geological evidence indicates liquid water existed early. That mismatch is a clue that habitability depends on atmospheric and geochemical buffering, not just distance from the star. The Chicxulub impact happened about 66 million years ago. Its timing matters because it shows that habitable does not mean safe. Earth can support life while still being periodically reshaped by catastrophes. The Chicxulub impactor was on the order of 10 kilometers across. That scale is large enough to drive global climate disruption through dust and aerosols, collapsing food webs. Earth's magnetic field strength near the surface is on the order of tens of microtesla. The number is small compared with human-made magnets, but the system scale effect is large. It shapes how the solar wind interacts with the upper atmosphere. The moon's average distance is about 384,000 kilometers. That distance matters because tides and Earth's rotational evolution depend on it, and because the moon's gravitational influence affects Earth's long-term orientation dynamics. Where it works and where it breaks, the rare events framing works best as a filter model. Many planets may pass some filters while failing others. A planet can have water but lose its atmosphere. It can have an atmosphere but lack long-term climate buffering. It can be in the habitable zone but be geologically stagnant. Where the framing breaks is when it turns into a single-story myth, like Jupiter protects Earth, or one asteroid made humans inevitable. Real planetary systems are dynamical. A configuration can reduce one kind of risk while increasing another. The model also fails if selection effects are ignored. We are observing from a planet that has successfully survived. That does not prove Earth is common or rare. It only proves that at least one chain worked. Analysis, scientific, and engineering reality. Earth's habitability is a complex system that involves energy balance, atmospheric chemistry, and interior dynamics. A habitable zone placement sets the baseline energy input, but greenhouse gases and clouds determine the actual surface state. Over long times, silicate weathering can draw down carbon dioxide when the planet warms and reduce drawdown when the planet cools, acting as a stabilizing feedback. The interior matters because it powers tectonics, volcanism, and the dynamo that generates the magnetic field. Without ongoing heat flow and core convection, you can lose both atmospheric recycling and magnetic shielding. What would falsify the comforting version of this story is evidence that Earth-like planets commonly keep oceans without plate tectonics, or that magnetic fields have little effect on long-term atmospheric retention. Some work already suggests the details are more nuanced than older one-factor saves everything narratives. Impact. If Earth's habitability depends on a chain of filters, then the search for life becomes an engineering and measurement problem. Detect which worlds pass which filters. That drives real markets. Exoplanet atmospheric characterization pushes telescope design, detectors, and data analysis pipelines. Planetary defense drives survey telescopes, orbit modeling, and impact risk infrastructure. Earth system science drives better climate models and geochemical monitoring. A practical adoption hurdle is uncertainty. Decision makers fund missions and infrastructure when the measurement logic is clear. What we can detect, how confidently, and what would change our minds. There are no meaningful privacy risks here. The plausible risks are strategic and interpretive. Strategically, planetary defense is a global coordination challenge. Sharing tracking data, agreeing on response plans, and resisting politicization of low probability, high impact threats. Interpretively, the big misuse risk is narrative overreach. Goldilocks zone headlines can imply life is likely, while rare Earth headlines can imply it is nearly impossible. Both can be wrong in ways that distort education, funding priorities, and public trust. Impact. This topic reshapes how people understand home. Earth is not merely a place. It is a historical achievement of physics plus time. It also reframes environmental thinking. If habitability is maintained by feedback loops that operate slowly, then rapid human-driven perturbations are not just pollution. They are shocks to the same stabilizing system that kept oceans liquid through deep time. In education, it offers a rare integrative story. Astronomy, geology, biology, and climate science are not separate chapters. They are one mechanism. Unknowns. Most coverage treats Earth's habitability like a checklist: right distance, water, atmosphere. The overlooked point is that the checklist items interact, and the interactions matter more than the items. Earth's luck is not only about initial conditions, it is also about survivability under drift. The sun brightens over time. Without a long-term carbon thermostat, Earth should either freeze early or overheat later. That means habitability is a moving target that must be actively stabilized by planetary processes. The second missed point is that life is not just a passenger. Once biology appears, it can amplify stability through carbon burial and atmospheric transformation, while also creating new fragilities, like dependence on oxygen levels, ozone shielding, and complex food webs. Why this matters? The people most affected are those living on the only known habitable planet, but the impacts vary in different locations. In the short term, the lesson is humility about stability. Earth's habitable state is resilient over geologic times, but it can be fragile on human timescales. In the long term, the lesson is direction for exploration. If we want to find life elsewhere, we should look beyond in the habitable zone and ask, does the planet likely have atmosphere retention, long-term climate buffering, and sustained energy and nutrient cycling? Milestones to watch are not single dates but capability shifts. Better atmospheric spectra for small rocky planets, better constraints on interior activity, and better assessment of impact populations and risks. Impact. A near-Earth asteroid survey team uses the same orbital mechanics that shaped Earth's impact history, turning existential risk into a measurable pipeline of detection, tracking, and probability updates. A climate researcher studying long carbon cycle feedback uses Earth's deep time thermostat logic to frame what is fast versus slow in climate responses and what kinds of change are hard to reverse. A space mission planner deciding where to search for life weighs habitability as interpretability. Can we measure enough about the environment to distinguish biology from non-biological chemistry? A science teacher uses Earth's oxygenation story to explain why complex life is not just more time, but also different atmosphere, and why biology can transform a planet. Frequently asked questions. What is the Goldilocks zone, really? The Goldilocks zone is the distance range from a star, where a planet could have surface liquid water if it has a suitable atmosphere. The Goldilocks zone serves as an initial filter, but it does not guarantee the presence of liquid water. Did the asteroid, that killed the dinosaurs make humans possible? It did not create mammals, but it likely changed ecological opportunity. By collapsing dominant ecosystems, it opened niches that allowed different lineages to radiate and reshape the biosphere. Is the moon necessary for life on Earth? Not provably. The moon likely influences tides and Earth's long-term orientation dynamics, and it may have helped stabilize conditions. However, the term necessary implies a stronger requirement than the available evidence supports. Why is plate tectonics often linked to habitability? This is due to its role in recycling carbon, regulating climate over extended periods, and replenishing nutrients. The question is whether Earth's specific style of tectonics is required, or whether alternative recycling regimes can do similar work. Could a planet be habitable without a magnetic field? Perhaps it would depend on the planet's atmosphere, gravity, and stellar environment. Magnetic fields can change how the solar wind couples to the upper atmosphere, but the details are complex, and it is not a single on-off switch. How did Earth stay warm when the young sun was dimmer? That is a classic puzzle that points to stronger greenhouse warming and different cloud and surface conditions early on, plus geochemical feedbacks that adjust atmospheric composition over time. Does rare Earth mean life is rare? Not necessarily. It can mean complex surface life like ours is rare, while microbial life could be more common. The answer depends on the number of filters that are genuinely difficult to overcome, compared to those that are simply not yet understood. Can life exist outside a star's habitable zone? Yes, in principle. Subsurface oceans heated by internal energy, chemical gradients, or tidal heating can host habitats even far from stellar warmth. The road ahead. Earth's habitability story is not a trophy. It is a diagnostic. It tells us what to measure, what to model, and how to stop oversimplifying. If we see more rocky planets with stable atmospheres and habitable zones, it could lead to a shift away from rare Earth narratives toward common beginnings, rare long-term stability. If we see that atmospheres are routinely stripped or destabilized, it could lead to a more pessimistic view of surface habitability around mini-stars. If we see strong signs that climate buffering can work without Earth-like plate tectonics, it could lead to a broader definition of habitable worlds. If we see that buffering correlates tightly with active geology, it could narrow the target list and raise the value of methods that infer interiors indirectly. What to watch next is the move from where could water exist to which worlds can stay habitable for billions of years. For more insight and less noise, subscribe and explore the full range at taylortaylor.co.uk.